Right now, the universe is growing at an almost unimaginable pace. Every second, the space separating distant galaxies increases by thousands of miles. Here's the mind-bending part. It isn't expanding into anything. There's no pre-existing emptiness waiting to be filled. No edge to cross. No container surrounding it. We're about to explore one of the most perplexing ideas in science: how space itself can come into existence from nothing. Reality stretches in ways that defy intuition, and asking what the universe expands into is just as futile as asking what lies north of the North Pole. Consider leaving a like and subscribing to the channel as we begin. Consider a simple analogy: blowing up a balloon in your living room. As air fills it, the balloon stretches outward, pressing against the surrounding space. It grows because there is room to expand. The air around it provides the extra space. Expansion in everyday life always requires somewhere to go. But the cosmos doesn't follow these familiar rules. When scientists say the universe is expanding, it's tempting to picture a balloon stretching into a void, with a clearly defined edge where something else begins. That image feels natural, but physics tells us it's wrong. The universe doesn't grow into anything. There's no exterior, no invisible walls, no extra space waiting. Instead, the expansion is the creation of space itself. Space comes into being as the universe enlarges. Here's another way to imagine it. Picture drawing a circle that's larger than your piece of paper. Rather than finding a bigger sheet, the paper itself stretches to fit the circle. In everyday life, expansion always happens into something. Trees grow into air, cities sprawl across land, ice spreads across water. Boundaries exist, and the expansion fills them. But with the universe, there's no separate container. The boundary and the expansion are inseparable. The growth of space is the boundary. Scientists uncovered this mind-bending truth by observing distant galaxies. Edwin Hubble noticed that galaxies farther away from us are moving away faster than those nearby. At first glance, it seems as if we're at the center of some cosmic blast, with everything shooting outward. But the reality is far stranger. It's not the galaxies moving through space. The space between them is stretching. Think of dots drawn on a balloon. As it inflates, the dots drift apart without moving across its surface. Each dot sees the others receding, but no dot occupies a central position. Now, imagine that same principle in 3 dimensions. The universe isn't expanding into anything because there's no outside. It's creating the stage on which its growth takes place. This idea defies intuition so completely that even the greatest minds struggled with it. Einstein himself initially rejected it. Yet this extraordinary expansion is happening right now, faster than we can fully comprehend. So how can we prove it? The answer comes from light itself. When a distant galaxy sends a beam of light toward Earth, that light has a specific wavelength, blue, red, or infrared, like a cosmic fingerprint. As it travels through expanding space, the wavelength stretches. Imagine walking on a moving walkway that stretches as you walk. Your steps remain the same, but the ground beneath grows longer, and by the time you reach the end, you've covered much more distance than your steps alone account for. Light behaves the same way. As it travels through stretching space, its wavelength lengthens. Blue light from a faraway galaxy arrives at our telescopes as red, not because the galaxy is speeding away, but because space itself expanded along its journey. This process, known as cosmological redshift, shows that space grows independently of the objects within it. And here's the astonishing part. Light from the farthest galaxies has been stretched nearly 40 times from its original wavelength. Radiation that began as intense ultraviolet now reaches us as faint infrared. That means the universe has expanded 40-fold since that light first set out on its journey. Consider this: the galaxy that emitted that ancient light appears small and faint in our telescopes. But when the light left, the universe itself was 40 times smaller than it is today. That galaxy was much closer to the region that would eventually become the Milky Way. Space didn't merely stretch a little, it underwent enormous, relentless expansion. But here's what truly twists the mind. This stretching isn't happening somewhere far away. It's occurring everywhere. Right now, the space in this very room is attempting to grow. Even the space between your eyes and this screen is trying to expand. You don't notice it because electromagnetic forces between atoms are immensely stronger than the rate of cosmic expansion. Only over vast intergalactic distances does the effect become observable. The space between galaxies is unbound by atomic forces, so it expands freely, carrying galaxies along like raisins in a loaf of rising bread. The raisins don't move through the dough. The dough itself grows, pushing them apart. This is why the question, "What is the universe expanding into?" falls apart. You are part of the dough. If space is stretching everywhere, then how far can we actually see? We live inside the ultimate cosmic prison, its walls built from time itself. Every night, when you step outside and gaze at the stars, it feels as though you are witnessing the universe in its entirety, stretched across the night sky. Yet in truth, you are seeing less than 4% of what exists. You are enclosed within an invisible sphere, roughly 46 billion light-years in radius. Beyond this boundary lies the rest of the universe. Billions of galaxies, trillions of stars, and perhaps even other versions of you reading these words. But none of it is accessible. No telescope, no conceivable technology can ever reveal it. The trap is not physical. It is born from the finite speed of light and the universe's finite age. Light takes time to travel. The sun appears to us as it was 8 minutes ago. Alpha Centauri as it was 4 years ago. Andromeda 2.5 million years ago. The farther we peer into space, the deeper into history we look. Here's where the prison tightens. The universe is 13.8 billion years old. Light from galaxies farther away than 13.8 billion light-years has not yet reached us. From our perspective, those galaxies might as well not exist. Yet the situation is even more complex. Space has been expanding since the universe began. That distant galaxy was much closer when it emitted the light we see today. By the time the light reaches us, cosmic expansion has carried the galaxy far beyond 13.8 billion light-years. Today, it sits roughly 46 billion light-years away. This defines the walls of your cosmic cell. Everything beyond 46 billion light-years lies in the unobservable universe. You cannot see it, detect it, or prove it exists. Logic and mathematics, however, insist it must be there. Imagine standing in dense fog that limits your vision to 100 yards. You can see a circle around yourself, yet you know the world continues beyond the mist. Your observable universe is that circle. The real universe stretches infinitely in every direction. Here's the number that should shock you. If the universe is infinite, your observable bubble contains 0% of what actually exists. What lies beyond the walls of this cosmic prison? The oldest light in the universe is racing toward you at nearly 600 million miles per hour. Carries a message from the very beginning of reality. This light has been traveling longer than Earth has existed, longer than our solar system formed, longer than our galaxy took shape. It began its journey when the universe was just 380,000 years old. a searing plasma where atoms could not yet form. This primordial radiation is the cosmic microwave background, filling every cubic inch of space. About 1% of the static on an old TV comes from this radiation. You are literally seeing the afterglow of creation flickering across the screen. This radiation marks the edge of everything we can observe. Before that moment, 380,000 years after the Big Bang, the universe was opaque. Imagine trying to see through the sun. Photons could travel only inches before colliding with charged particles. Then the universe cooled enough for protons and electrons to combine into hydrogen atoms. The cosmic fog lifted. Light could travel freely, and those first photons are what we now detect as the cosmic microwave background. This event, called recombination, created the ultimate observational horizon. Nothing from the first 380,000 years is ever visible. It remains forever hidden behind a cosmic wall. Here's the mind-bending part. This horizon grows with every passing second. Light that has traveled 13.8 billion years plus 1 second reaches us, adding roughly 186,000 miles of new visible universe each second. Every day, we can see about 16 billion miles farther into the cosmos. But expansion complicates this picture. While the observable horizon grows, the sources of that light are moving even farther away due to cosmic expansion. A galaxy that emitted a photon 13 billion years ago now lies roughly 30 billion light-years away. We see it as it was, not as it is. It's like watching someone walk away while the screen of your movie keeps enlarging. The cosmic microwave background reveals a universe smoother than a polished mirror, with temperature differences of only a few millionths of a degree. These tiny variations eventually became the structures we see today. But what lies beyond this horizon? Past the edge of everything we can see lies more of what we already observe. More galaxies, more stars, more planets, possibly more life. The universe appears homogeneous at its largest scales. Homogeneous means uniform, the same everywhere, like perfectly mixed cake batter. Observations of the cosmic microwave background confirm this property. Tiny temperature differences are smooth and consistent across the entire sky. This smoothness implies something profound about the universe beyond our view. If the observable universe contains roughly 2 trillion galaxies, a region of identical size just beyond our horizon should contain another 2 trillion galaxies. And yet another region beyond that should contain another 2 trillion, and so on, an endless repetition stretching across the infinite cosmos. The pattern repeats endlessly, or at least far beyond anything we can truly grasp. But this idea introduces a deeply unsettling concept. If space is genuinely infinite and uniform, then every possible arrangement of matter within any given volume must occur somewhere, again and again. This isn't a matter of speculation or mysticism. It's a mathematical inevitability. With an infinite expanse of space and only a finite number of ways to arrange a finite set of particles, repetition becomes unavoidable. Imagine shuffling a deck of cards an infinite number of times. Eventually, the same arrangement must appear more than once. The universe operates on a similar principle, except it uses atoms instead of cards. This implies that there are other versions of you somewhere, reading these words at this very moment. Not figuratively, but literally. In regions of space so distant that their light will never reach us, quantum mechanics has arranged matter in every conceivable configuration, including configurations identical to your own. There are versions of you who stopped reading at this sentence, versions who were never born, and versions in which the entire history of Earth unfolded differently. Mathematics suggests these duplicates exist at mind-boggling distances, approximately 10 to the power of 10 to the power of 115 meters away. That number is so large that, If you tried to write it out, the line of digits would extend across more space than exists in the observable universe. And yet, if space is infinite, these distances are still finite. Somewhere out there, another version of you is having this same realization about yet another version, even farther away. But all of this assumes that the universe beyond our observable horizon mirrors the universe we can see. What if it doesn't? Recent observations hint that our local region may be unusual. We appear to exist in a cosmic void, an area with a lower than average density of galaxies. Beyond our observable horizon, the universe could contain denser regions brimming with galaxies, black holes, and intense activity, or it could reveal vast, near-empty expanses. Some theoretical models of cosmic inflation, the extremely rapid expansion that occurred during the universe's first fraction of a second, suggest that other regions might operate under vastly different physical laws. These pocket universes could have different particle types, different constants, or even completely different rules of physics, rendering our textbooks useless in those regions. Yet there is an even deeper question lurking beneath all of this speculation. What if the universe is not infinite at all? An infinite, expanding universe presents one of the most beautiful and paradoxical concepts in physics. How does one make infinity bigger? Mathematics tells us it should be impossible. Infinity plus anything is still infinity. Infinity multiplied by any number is still infinity. You cannot add to something that already contains everything. And yet, observations show clearly that space is expanding everywhere. The resolution comes from understanding what expansion truly means. When scientists say the universe is expanding, they do not mean it is becoming more infinite. Instead, they mean that the scale of space itself is increasing. Picture an infinite sheet of graph paper where each square is 1 inch wide. Now imagine stretching that paper so that each square becomes 2 inches across. The paper is still infinite, with infinitely many squares, but the distance between any two marked points has doubled. This is precisely what happens during cosmic expansion. The universe does not become more infinite. The scale of space grows, and all distances expand proportionally. A galaxy that is 100 million light-years away today was only 50 million light-years away when the universe was half its current size. This leads to a profoundly disturbing implication. If the universe is infinite now, it must have been infinite at the moment of the Big Bang. The Big Bang, then, was not an explosion from a single point into empty space. It was the simultaneous expansion of infinite space, filled with energy everywhere. Wrap your mind around that. The Big Bang happened everywhere at once across infinite space. There was no center, no edge, no outside, only infinite space beginning to expand and cool. Every point in the universe can claim to be the center because the expansion appears identical from every location. This infinite perspective solves some cosmic puzzles while introducing others. It explains why the universe looks uniform in all directions from our vantage point. In an infinite, homogeneous space, all locations are equivalent. It also accounts for why we cannot detect an edge or a center, because none exist. But it raises a haunting question. If the universe contains infinite matter and energy, how do we avoid infinite density? The answer lies in the definition of density: matter divided by volume. Even if both matter and volume are infinite, their ratio can remain finite. The universe can contain infinite stuff spread across infinite space while maintaining an average density of approximately 5 hydrogen atoms per cubic meter. Here's where the paradox becomes deeply personal. In an infinite universe, every possible event not only happens, but happens infinitely many times. Not just the repetitions of you we discussed earlier, but every possible story, every scenario, every outcome. Every triumph, every tragedy, every moment of beauty, and every act of cruelty occurs somewhere in the infinite expanse. If this seems unsettling, consider the alternative. A finite universe poses equally troubling questions. What lies beyond its edge? How could space itself have a boundary? What would happen if you tried to travel past it? These conceptual difficulties are why many scientists favor models of an infinite universe. Observations of the cosmic microwave background suggest that the universe is either infinite or so large that any curvature is undetectable. The simplest explanation is that space extends infinitely in all directions. This means that the expansion we observe is not the creation of new space in the sense of adding rooms to a house. It is the stretching of the infinite fabric that already exists. But if space is not being created in a conventional sense, what drives this relentless expansion? The answer lies in the universe manufacturing new space from pure nothingness. Every second, the volume of observable space increases by roughly 10 to the power of 78 cubic meters. That number is so vast that counting it 1 unit per second would require more time than the universe has existed, multiplied by itself billions of times. All of this new space emerges from the quantum vacuum. Quantum vacuum is far from the empty void one might imagine. It is a seething foam of virtual particles that appear and annihilate in intervals shorter than the smallest measurable instant. This process, known as quantum fluctuation, fills every point in space with energy. Even in the most perfect vacuum, this quantum activity never ceases. Here is the truly mind-bending part. Vacuum energy has gravitational effects. But unlike ordinary matter, which attracts, vacuum energy creates repulsive gravity, pushes space apart. The more space there is, the more vacuum energy it contains. The more vacuum energy there is, the faster space expands. This runaway feedback loop is called inflation. During the universe's first tiny fraction of a second, this process ran absolutely wild. Space expanded faster than light could travel, not because anything moved faster than light, but because space itself stretched beyond light's reach. Imagine trying to walk across a treadmill accelerating faster than you could run in less than a trillionth of a trillionth of a trillionth of a second. A region smaller than a proton ballooned to roughly the size of a basketball. It sounds like science fiction, yet quantum mechanics demands it. The uncertainty principle allows energy to be borrowed from the vacuum, provided it is repaid quickly enough. During inflation, the universe borrowed massive amounts of energy to generate new space and then used the expansion itself to repay the debt. It is like taking out a loan to buy a money printing machine and then using the printed money to pay off the loan. The process overshot its original purpose, creating far more space than necessary. Our entire observable universe represents only a tiny patch of this vastly larger inflated region. Imagine inflating a balloon to the size of Earth, then examining a pinhead-sized patch. That pinhead is our observable universe in comparison. And here's the truly surreal part. This process continues today. Modern expansion, though slower than inflation, operates on similar principles. Dark energy, which constitutes roughly 68% of all energy in the universe, behaves like vacuum energy. It fills space uniformly and produces repulsive gravity, accelerating expansion. As the universe grows, more dark energy appears to occupy the new space. This seems to defy our intuition about energy conservation, yet the laws are preserved. Gravitational potential energy is negative. As matter spreads out, its gravitational energy decreases, balancing the positive energy of the newly created dark energy. The universe maintains perfect energy equilibrium while producing infinite new space. This process will continue indefinitely, or at least far longer than human minds can comprehend. Every passing moment brings with it new space, new dark energy, and an ever-accelerating expansion. The universe grows not because it requires somewhere to expand into, but because expansion itself generates its own room. Yet even all this cosmic creativity pales in comparison to what occurred during that first fraction of a second. But how do we know that this seemingly impossible story actually unfolded? The evidence is hidden in the static of old television sets, the quiet hiss that spoke volumes about the most violent event in cosmic history. In 1964, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were attempting to eliminate persistent background noise from their antenna. They cleaned bird droppings from the equipment, recalibrated their instruments, and aimed the antenna in multiple directions. But the hiss never disappeared. That static was the echo of creation itself. What they had stumbled upon was the cosmic microwave background, the afterglow of the Big Bang stretched and cooled over 13.8 billion years of cosmic expansion. This discovery earned them the Nobel Prize and provided the most direct evidence for the universe's expansion. The cosmic microwave background is so crucial because it carries the imprint of cosmic expansion, literally encoded in its wavelengths. When this light first escaped the early universe, it shone as brilliant visible light at roughly 3,000 degrees. But as the universe expanded, the wavelengths stretched alongside space itself. Intense visible photons became infrared radiation, then microwaves, and eventually faint radio waves. Today, this primordial light arrives at a mere 2.7 degrees above absolute zero. The background is astonishingly uniform, differing by only a few parts in 100,000. A precision that confirms the early universe was extraordinarily smooth, exactly as inflation predicts. Yet the tiniest temperature variations that do exist tell an even more extraordinary tale. These minuscule ripples are the quantum fluctuations that inflation magnified from subatomic scales to cosmic proportions. Those microscopic differences became the seeds of galaxies, stars, and planets. Your very existence is a product of quantum uncertainty magnified by cosmic expansion. Advanced satellites, including the Cosmic Background Explorer and Planck, have mapped these variations in exquisite detail. From this ancient light, cosmologists can measure fundamental properties of the universe with remarkable precision. The geometric flatness of space, the proportion of ordinary matter, just 5%, and the precise rate of cosmic expansion. The cosmic microwave background also reveals the universe's extreme compression in its earliest stages. Today's observable universe, every galaxy and star visible through our most powerful telescopes, was once confined to a region no larger than a beach ball. This compression wasn't about stuffing matter into a small container. Space itself was compressed. The beach ball didn't contain the early universe. It was the early universe. There was no outside, no surrounding space, just that compressed patch of space-time beginning its expansion into the vast cosmos we inhabit today. This realization raises a profound question. What provided the energy to drive such dramatic expansion? The answer points to a force that constitutes more than 2/3 of the cosmos yet remains entirely invisible. Dark energy. How do you detect something that hides in plain sight? In 1998, two teams of scientists set out to measure whether the universe's expansion was slowing under gravity's influence, but instead discovered that expansion is accelerating. This groundbreaking finding earned a Nobel Prize and overturned decades of assumptions. For generations, astronomers believed that gravity would eventually win, gradually slowing expansion until galaxies either stopped moving apart or collapsed back together. To test this, scientists studied a special type of supernova, type Ia, whose explosions are almost identical in brightness, making them reliable cosmic lighthouses. By comparing observed brightness with predicted brightness, astronomers could measure precise distances to distant galaxies. The results were astonishing. These supernovae appeared fainter than expected, indicating they were farther away than the standard expansion model predicted. Space had grown more than it should have during the light's journey, proving that expansion is accelerating. The culprit behind this mysterious acceleration is dark energy. It dominates roughly 68% of the universe's total mass energy content, outweighing all ordinary matter by a factor of more than 13 to 1 and exceeding even dark matter, the invisible framework holding galaxies together. Yet its nature remains a profound mystery. Unlike matter, which dilutes as space grows, dark energy maintains a constant density, continuously filling newly created space. Its influence increases as the universe expands. In the early universe, matter and radiation controlled cosmic evolution. Dark energy existed but had negligible effects compared to the gravitational pull of dense matter. As expansion thinned matter, dark energy's repulsive power became more prominent. About 5 billion years ago, roughly when our solar system formed, dark energy became the dominant force, reversing the universe's previous slowing expansion. Today, we live in an era of acceleration. Each day, expansion grows slightly faster. Each moment, dark energy's influence strengthens. In the distant future, this effect will become extreme. Galaxies will recede faster than light can travel between them, vanishing from the observable universe forever. But what exactly is this invisible force? The leading candidate is vacuum energy, the energy of quantum fluctuations present at every point in space. Quantum field theory predicts enormous amounts of vacuum energy, yet calculations overshoot observed values by a factor of 10 to the power of 120, the largest discrepancy in the history of physics. Either quantum mechanics is incomplete, or some mechanism cancels most of this energy, leaving just enough to drive cosmic acceleration. Alternative theories propose dark energy might be a new field permeating space, akin to the electromagnetic field, or that gravity behaves differently at cosmic scales. Regardless, dark energy shapes the destiny of the cosmos, driving an acceleration that began in earnest during an even more dramatic epoch, cosmic inflation. In the first trillionth of a second after the Big Bang, the universe expanded faster than light could traverse distances between points. Inflation tore regions apart, severing causal contact forever. Nothing can move through space faster than light, but space itself is unrestricted. During inflation, distances doubled repeatedly in such rapid succession that light couldn't keep up. Imagine two ants on a balloon inflating so fast that they can never reach each other, no matter how fast they move. Here's a mind-bending number. Inflation expanded the universe by at least a factor of 10 to the power of 26, turning something smaller than a grain of sand into a volume larger than the observable universe today, all within 10 to the power of -35 seconds. To put this in perspective, light travels about 1 foot in a nanosecond. During inflation, space expanded so rapidly that light would have crossed less than the width of a proton. The energy powering this expansion came from the inflaton field, a hypothetical quantum field permeating space. Unlike ordinary fields, whose minimum energy is zero, the inflaton became trapped in a high-energy false vacuum, creating a temporary form of dark energy far stronger than what exists today. This false vacuum drove exponential growth, initially slow, then accelerating dramatically. To visualize, folding a sheet of paper in half 42 times would produce a thickness equal to the distance to the moon. inflation was far more extreme. In every infinitesimal instant, space doubled again and again. Inflation solved major cosmological problems while creating new mysteries. It explains the uniformity of the cosmic microwave background. Without inflation's rapid smoothing, regions of the observable universe would display wildly different temperatures. Inflation also accounts for why space appears geometrically flat. Any initial curvature was stretched to near invisibility, like inflating a basketball until its surface seems flat from your tiny perspective. But perhaps most profoundly, inflation amplified quantum fluctuations, setting the stage for the universe we inhabit today. During inflation, tiny quantum fluctuations within the inflaton field were stretched from subatomic scales to cosmic proportions. These minute variations in energy density became the seeds that ultimately grew into galaxies, stars, and planets. Every structure in the universe, including the Milky Way, our sun, and even the atoms in your body, traces its origins to random quantum events amplified during the universe's first moments. In essence, you are the product of quantum foam. But inflation also raises a chilling possibility. If it occurred once, it could happen again. The very quantum fields that triggered primordial inflation may still exist, dormant, waiting for the right conditions to spark another episode of exponential expansion. Such an event could ignite anywhere, at any moment, generating a new inflationary bubble that expands at the speed of light, annihilating everything in its path. Within this bubble, the laws of physics as we know them would collapse, atoms would disintegrate, and the universe would be unrecognizable, all without warning. Even more mind-bending is inflation's implication that our universe might be just one bubble in an endless cosmic sea of expanding realities. While you read these words, trillions of other universes could be inflating into existence, each governed by its own set of physical laws, constants, and possibilities for life. This is not science fiction, it's a direct consequence of inflation theory. Quantum mechanics dictates that inflation, once triggered, can occur repeatedly across a larger multiverse, with random fluctuations spawning countless bubble universes. Each bubble evolves independently, forming galaxies, stars, and planets, while our own universe is just one among infinite others. This multiverse scenario carries profound consequences. Every bubble may possess entirely different physics. Gravity might be stronger or weaker, electrons heavier or lighter, or the number of spatial dimensions different from 3. Most bubbles would be inhospitable. In some, gravity might crush stars instantly into black holes. In others, matter may never clump into structures. Some universes could lack electromagnetic forces, making chemistry impossible. Others might remain eternally inflating, never cooling enough for atoms to form. But in an infinite multiverse, even the most improbable configurations must exist somewhere. No matter how unlikely the combination of physical constants that allows life in our universe, infinite opportunities ensure they occur in at least one bubble. We exist not because our universe is special, but because observers can only arise in habitable bubbles, a principle known as the anthropic principle. Yet this idea challenges our sense of uniqueness. If infinite universes exist, every possible event occurs somewhere. Every choice you avoided is realized by another version of you elsewhere. Every dream unfulfilled in this universe is realized in another. Infinite replication renders individuality meaningless. You are not unique if infinite versions of you exist, and every choice you make inevitably occurs elsewhere. Your universe is just one among infinitely many similar realities. The multiverse, however, is fundamentally unobservable. Other bubble universes lie beyond our cosmic horizon. Their light will never reach us. Their gravitational influence cannot touch us. and their existence cannot be proven. Many scientists question whether untestable theories like this qualify as science. Yet the mathematics of inflation strongly points toward eternal inflation and ongoing bubble formation. Quantum field equations that explain our universe's early expansion also predict continuous creation of new bubbles. If inflation occurred, we must contend with its implications. Recent observations provide indirect support. The cosmic microwave background carries subtle patterns that align exquisitely with inflation predictions. These observations strengthen confidence in inflation and, by extension, hint at the possible existence of a multiverse. But even this staggering concept assumes the universe has only the 3 dimensions of space we experience. Modern physics suggests reality could be far stranger. What if expansion occurs along directions invisible to us? String theory, our leading candidate for unifying all physics, requires 9 spatial dimensions instead of 3. 6 extra dimensions may exist here and now, compacted so tightly that even particles cannot detect them. These hidden dimensions could be expanding alongside the familiar 3. Imagine an ant walking along a garden hose. From its perspective, it can move forward or backward, experiencing a single dimension. Yet the hose has 3 dimensions, including circular ones around its surface, too small for the ant to perceive. Similarly, we may be aware of only 3 spatial dimensions while 6 others remain curled up beyond our perception. If these extra dimensions exist, they might answer the question, what does the universe expand into? Our 3-dimensional space could be expanding within a higher dimensional hyperspace, like a balloon inflating in a room. This idea, called the brain world model, posits that our entire universe is a 3-dimensional membrane, with gravity alone able to access the higher dimensional space. The expansion we observe could reflect the stretching of our brain within this larger hyperspace. Even stranger, other brains could exist nearby, parallel to ours in extra dimensions. A version of you might be reading these words just a millimeter away in a 4th spatial dimension. Collisions between brains could trigger phenomena we interpret as Big Bangs. The cosmic microwave background might then be the afterglow of such a brain collision, providing energy for inflation and setting our universe on its current expansion trajectory. Every few trillion years, additional collisions could restart cosmic evolution in entirely new universes. Some theoretical models even suggest hidden dimensions themselves expand while our familiar 3 remain static. From our perspective, space appears to grow, but the expansion is actually occurring in dimensions we cannot perceive. Think of a balloon whose surface does not change while the interior swells. We, confined to the surface, would never directly detect the interior's expansion. Other models propose that some dimensions expand while others contract, so the total volume of space remains constant even as our slice appears to grow. These possibilities are highly speculative. The Large Hadron Collider searches for evidence of extra dimensions by looking for particles disappearing into hyperspace, but so far none have been detected. Even so, string theory's mathematics continues to indicate that extra dimensions are essential for a complete understanding of reality. If they exist, the universe may be expanding into unseen directions beyond human perception. Even if extra dimensions do not exist, the geometry of our familiar 3-dimensional space could hold surprises. Space might curve back on itself, rendering the question of what it expands into meaningless. The universe could be shaped like a donut, with expansion merely increasing the donut size. Local geometry could remain flat, while the overall topology is finite and closed. General relativity allows 3 possibilities for space's shape. Flat space, like an infinite sheet of paper, where parallel lines never meet and triangle angles sum to 180 degrees. Closed space, like a sphere, where parallel lines converge, triangle angles exceed 180 degrees, and traveling straight could eventually return you to your starting point. Open space, like a saddle, where parallel lines diverge, triangle angles are less than 180 degrees, and space stretches infinitely with negative curvature. Current data suggests the universe is nearly flat, though flatness does not guarantee infinitude. A flat sheet of paper can be rolled into a cylinder or connected to form a donut shape. Locally, it appears flat, but globally, it is finite. If space wraps onto itself, asking what it expands into becomes meaningless. The expansion is simply the shape enlarging. Such a topology would produce observable signatures. In a donut-shaped universe, light could traverse the universe and return to its origin, producing multiple images of the same distant galaxies in different directions. Patterns in the cosmic microwave background could repeat as light circumnavigates the universe. Astronomers have searched for such signatures, but so far, none have been observed. Either our universe is vastly larger than the observable region, or it doesn't wrap around itself at scales we can detect. Perhaps it is a donut, but one so immense that light has not yet had time to complete a single loop. Yet the question of shape becomes even more complex when we consider that space and time form a single, four-dimensional fabric. The universe's geometry is not just spatial, it includes time. Expansion stretches not only space but also the relationships between space and time throughout the cosmos. In the early universe, when everything was compressed, time itself flowed differently than it does today. Clocks would tick at different rates, and simultaneity across vast distances would have a radically different meaning. As space expands, it drags time along. This coupling of space and time creates effects that defy intuition. Distant galaxies recede from us faster than light, not because they move through space, but because space itself carries them away, stretching both spatial and temporal dimensions. From their perspective, they remain stationary while we speed away. Expansion looks the same from every vantage point, so every observer perceives themselves at the center. There is no preferred frame, no absolute center, no outside to expand into. The universe grows by becoming more itself, not by entering some external space. Yet this philosophical resolution of the expansion paradox introduces new questions about the nature of time. If space stretches, does time stretch too? Observations say yes. Einstein revealed that space and time are united into spacetime, so stretching one affects the other. Light from distant galaxies illustrates this vividly. A supernova that brightens and fades over 3 weeks in a nearby galaxy may appear to unfold 10 times more slowly in a galaxy at the edge of the observable universe. This is because the light carrying information about the event is stretched along with space, extending the intervals between photons. The universe literally stretches time itself. In regions moving rapidly away, time crawls. Consider this: light from the farthest galaxies is redshifted by a factor of about 10, indicating recession at roughly 90% of the speed of light when the light was emitted. Events in those galaxies appear 10 times slower than in our local frame. From their vantage point, our region of space would seem much younger. Cosmic expansion has stretched both space and time, compressing the early universe not only spatially but temporally. Processes that now take billions of years occurred far faster in the dense, young cosmos. The first stars, galaxies, and black holes formed in a universe where time flowed differently. Expansion also disrupts the concept of simultaneity across cosmic distances. In daily life, now seems universal, but relativity and cosmic expansion shatter this notion. What appears simultaneous to one observer occurs at different times for others. The present moment is local, not universal. As expansion accelerates under the influence of dark energy, these temporal distortions intensify. Distant events will appear increasingly frozen. Future civilizations will see time dilation more extreme than we can currently observe. Eventually, remote events will seem static. This relentless acceleration also drives the universe toward its ultimate fate: heat death. Expansion will spread matter and energy so thin that no process capable of generating usable energy can occur. In about 100 billion years, the last stars will exhaust their fuel, leaving only cold remnants. Beyond 10 to the power of 34 years, protons will decay, erasing all familiar matter. Only electrons, positrons, and photons will remain. After 10 to the power of 100 years, even black holes, the universe's last energy reservoirs, will evaporate via Hawking radiation. Supermassive black holes will linger longest, but eventually they too vanish. At this point, the universe reaches maximum entropy, a lifeless, uniform void at nearly absolute zero, incapable of supporting any process, reaction, or life. Even before this distant end, expansion poses a subtler threat. As space stretches, distant galaxies recede beyond our observable horizon. They don't vanish, they simply move too quickly for their light to reach us. In roughly 150 billion years, only our local group of galaxies will remain visible. Future astronomers may observe a universe devoid of cosmic expansion, with no cosmic microwave background and no trace of the larger universe. Yet an even more profound question emerges. What fills the empty vacuum that dark energy calls home? Empty space is far from empty. At the tiniest scales, it is a boiling cauldron of activity, far more violent than the sun's core. Space is alive with virtual particles, appearing and annihilating so rapidly that direct detection is impossible. This quantum foam permeates every cubic centimeter of seemingly perfect vacuum. Zoom in below atomic nuclei, down to the Planck scale, 10 to the power of -35 meters, and space dissolves into frothy, turbulent geometry. Virtual particles borrow energy from the vacuum, then annihilate with their antimatter partners almost instantly, obeying Heisenberg's uncertainty principle. Electron-positron pairs exist for 10^-21 seconds before vanishing, while heavier particles flicker into existence and disappear even faster. Every possible type of particle allowed by quantum field theory emerges in this restless vacuum, creating measurable effects. One striking example is the Casimir effect. Place two metal plates extremely close in a vacuum. Virtual particles with wavelengths larger than the gap cannot exist between the plates, while longer wavelength particles exist outside. This imbalance pushes the plates together, demonstrating that we can literally feel the pressure of the quantum vacuum. Cosmologically, this quantum foam matters profoundly. It is the engine of dark energy, the driving force behind the accelerated expansion that will shape the universe for all eternity. Every bubble of space, every flicker of quantum activity, contributes to the relentless stretching of the cosmos, guiding its destiny toward the cold, empty, yet profoundly complex void of the far future. All these virtual particles contribute to the energy density of empty space. When physicists calculate how much energy the vacuum should contain, they get an absurdly large number, so large that space would expand far faster than we observe. In fact, the vacuum should contain roughly 10 to the power of 120 times more energy than the dark energy we measure today. This discrepancy represents one of the most embarrassing failures in theoretical physics. Either our understanding of quantum mechanics is deeply incomplete, or some unknown mechanism cancels out almost all of the vacuum energy. Resolving this vacuum catastrophe could also explain dark energy. Perhaps the tiny fraction of vacuum energy that remains uncancelled drives the cosmic acceleration we observe. Maybe the universe suppresses most quantum foam while leaving just enough active to power expansion. Alternatively, our entire conception of vacuum energy could be misguided. Hidden fields might permeate space, extra dimensions could allow energy to leak away, or the very notion of empty space might be an illusion. Some theories even propose that space is made of something tangible. Loop quantum gravity suggests space is composed of tiny discrete units, linked like atoms in a crystal. String theory envisions space emerging from vibrating strings in higher dimensions. In both cases, empty space has structure. Expansion might stretch these components rather than create nothingness, meaning space doesn't expand into nothing. It is itself a something we are only beginning to understand. Yet even our ignorance about the vacuum pales in comparison to what might happen if expansion accelerates without limit. In roughly 22 billion years, dark energy could become so dominant that it tears apart every atom in the universe. This catastrophic end, known as the Big Rip, would make heat death seem gentle by comparison. Instead of a slow fading over trillions of years, the universe would destroy itself in a violent final spasm of accelerating expansion. The timeline of the Big Rip is terrifyingly precise. About 1 billion years before the end, dark energy overpowers gravity on galactic scales. Galaxy clusters dissolve as space stretches faster than gravity can hold them together. 200 million years before the finale, expansion rips apart individual galaxies. Stars scatter into isolation, and galaxies like the Milky Way and Andromeda disintegrate. 30 minutes before the end, solar systems unravel. Earth is torn from the sun, the moon drifts away, and every planet is left alone in dark, expanding space. In the final moments, the destruction accelerates. 90 seconds before the Big Rip, molecular bonds break. Atmospheric gases disperse, and oceans evaporate, not from heat, but because space stretches faster than intermolecular forces can maintain cohesion. 10-12 seconds before the end, atomic nuclei themselves disintegrate as the strong nuclear force succumbs to the relentless expansion. Matter reverts to fundamental particles, and at the moment of the Big Rip, even space and time may lose meaning. Some models suggest that beyond a certain threshold, distance itself becomes undefined, causality breaks down, and the universe becomes physically meaningless. This grim scenario depends on dark energy increasing over time. If dark energy remains constant, the Big Rip never occurs. The universe gradually approaches heat death instead. Current observations indicate that dark energy has been roughly constant, but data isn't precise enough to rule out slow changes. Future measurements of distant supernovae and other cosmic distance indicators may reveal whether dark energy strengthens, allowing cosmologists to calculate exactly when a Big Rip could occur. Conservative estimates place it around 22 billion years in the future, though more aggressive models suggest it could happen within a few billion years. Yet even this ultimate destruction might not be the absolute end. Some theories suggest that the tearing of spacetime during a Big Rip could trigger new cosmic inflation, spawning fresh universes from the remnants of the old. The disassembly of reality might seed entirely new bubbles of existence. To understand these cosmic futures, scientists must first measure the expansion that drives them. The story of cosmic expansion began with observation, not theory. How can we measure the stretching of space itself? Astronomers turn exploding stars into cosmic yardsticks, using their predictable brightness to map the growth of space. Type Ia supernovae are crucial. These explosions occur when white dwarfs accumulate too much matter from companion stars, releasing nearly identical energy regardless of location. By comparing observed brightness to intrinsic brightness, astronomers determine distances. Simultaneously, the redshift of the host galaxy reveals how much light stretches during its journey through expanding space. Plotting distance versus redshift across hundreds of supernovae reveals the expansion history. Distant supernovae appear fainter than expected under constant expansion, indicating that space has been accelerating due to dark energy. Supernovae are just one rung on the cosmic distance ladder. Nearby parallax measurements calibrate distances to stars within a few hundred light-years. These calibrate Cepheid variable stars, which pulsate in direct proportion to their intrinsic brightness. Cepheid distances extend the ladder to 100 million light-years, which then calibrates supernova measurements reaching billions of light-years. Despite the vulnerability of each rung to errors, multiple techniques confirm the same key result. The universe is expanding, and expansion is accelerating. This observational framework is formalized mathematically using the scale factor A(t). The scale factor encodes how distances change over time. When it doubles, distances double. When it triples, distances triple. By convention, the scale factor equals 1 today. Observing a galaxy with redshift z reveals the scale factor at emission. A equals 1/1 plus z. Light from the cosmic microwave background has z is almost equal to 1090, meaning the universe was 1,000th its current size when that light was emitted. Coupling the scale factor with Einstein's field equations allows prediction of the future. If the scale factor grows linearly, expansion is constant. Faster than linear, it accelerates. Slower, it decelerates. Observations show acceleration for roughly 5 billion years, consistent with dark energy dominance. The scale factor framework also encodes the universe's composition: 68% dark energy, 27% dark matter, and 5% ordinary matter. As space expands, matter dilutes, but dark energy remains constant, eventually driving near-exponential expansion. Remarkably, this understanding ties back to Einstein. In 1917, he introduced the cosmological constant to allow for a static universe, counteracting gravity with repulsive vacuum energy. When Hubble discovered the universe was expanding, Einstein called the term his greatest blunder. Yet in 1998, accelerating expansion was discovered. The cosmological constant turned out to describe dark energy perfectly. Modern observations suggest each cubic centimeter of vacuum contains 10⁻10 joules of dark energy, small yet vast across cosmic volumes. The irony is profound. Einstein added lambda to prevent expansion, removed it after Hubble's discovery, and today it explains the very acceleration he sought to avoid. The tiny but non-zero energy of empty space dominates cosmic evolution. Yet it also poses the vacuum catastrophe. Quantum mechanics predicts vacuum energy 10 to the power of 120 times larger than observed. Resolving this might require entirely new physics, or a dynamic field instead of a constant. Einstein's blunder became his most prescient insight, and it all began with Edwin Hubble's observations in 1929, when measuring galaxy distances and velocities accidentally revealed that the entire universe is flying apart. From there, the story of cosmic expansion and our understanding of the ultimate fate of the universe unfolds. Working at Mount Wilson Observatory with the largest telescope in the world, Hubble was trying to resolve a debate about the nature of spiral nebulae. Were these cloudy formations part of our Milky Way, or were they entirely separate galaxies at immense distances? His measurements confirmed the latter. They were separate galaxies. Yet that wasn't the most groundbreaking revelation. By using Cepheid variable stars as distance markers, Hubble calculated that these spiral galaxies lay millions of light-years away, far beyond the Milky Way's boundaries. This discovery expanded the known universe from a single galaxy to a cosmos teeming with countless galaxies. As Hubble plotted galaxy distances against their velocities, a startling pattern emerged. Every galaxy was moving away from us. Not just a few, not just the distant ones. Every single galaxy measured showed redshifted light, signaling recession from the Milky Way. At first glance, this seemed to place Earth at the center of a cosmic explosion. More perplexing still, the farther a galaxy was, the faster it appeared to recede. Galaxies twice as far moved twice as fast. 3 times farther moved 3 times faster. This relationship, now known as Hubble's law, suggested a direct proportionality between distance and velocity. Initially, Hubble interpreted this as actual motion through space, imagining galaxies racing away from us like debris from an explosion. But this view implied Earth occupied a special central position in the cosmos, violating the Copernican principle. The resolution came with the understanding that space itself is expanding. Picture dots on a deflating balloon. If you reverse the process, inflating the balloon causes every dot to move away from every other dot. The farther apart 2 dots are, the faster they separate. Yet no dot is at the center. This insight transformed Hubble's discovery. Galaxies aren't moving through space. Space itself is stretching, carrying galaxies along like raisins in rising dough. Hubble's law became the first observational evidence of an expanding universe. The proportionality constant, the Hubble constant, measures the rate of space expansion. Hubble's original values overestimated this rate, suggesting a universe only 2 billion years old, too young for Earth. The error arose from confusing 2 types of variable stars, leading to underestimated distances. Correcting this placed the universe's age comfortably above Earth's, while the distance-velocity relationship remained robust. Modern measurements confirm that Hubble's law applies consistently across billions of light-years, proving that expansion is a global property of space itself. Hubble's work also established the first cosmic distance scale, transforming astronomy from a 2-dimensional mapping of the sky into a 3-dimensional exploration of the universe. His discovery fundamentally changed our understanding of humanity's place in the cosmos. We don't inhabit a static, eternal universe. We live in a dynamic, evolving cosmos that began in a hot, dense state and has been expanding and cooling ever since. Yet Hubble's law raised a profound question. What is the ultimate fate of the universe? Would expansion continue indefinitely, or would gravity eventually halt it, causing collapse? The answer depends on the total matter density, leading to one of cosmology's deepest mysteries. There exists a critical density, about 5 hydrogen atoms per cubic meter, that determines whether the universe expands forever or eventually collapses. This almost perfect emptiness governs everything. The physics comes down to a competition between expansion and gravity. Expansion spreads matter across ever larger volumes. Gravity pulls matter together. If the universe exceeds critical density, gravity wins and expansion halts, leading to a big crunch. If it falls below critical density, expansion wins, eventually approaching heat death. Exactly at critical density, expansion slows asymptotically towards zero without ever stopping, a perfect cosmic balance. Measuring the universe's density became a central goal of cosmology. But most matter is invisible. Galaxy rotation curves revealed galaxies contain far more mass than visible stars suggest. This unseen mass, dark matter, interacts only via gravity, outweighing ordinary matter by over 5 to 1. Including dark matter brought the universe to roughly 30% of critical density, predicting eternal expansion. Then came dark energy, which changes the dynamics entirely. Unlike matter, dark energy produces repulsive gravity, accelerating expansion. Its presence makes the concept of critical density more complex. Yet current observations indicate our universe has about 27% dark matter, 68% dark energy, and 5% ordinary matter. Accounting for dark energy's negative pressure, we live remarkably close to critical density. This near balance creates the flatness problem. Why is the universe so finely tuned? Cosmic inflation offers a solution. Rapid early expansion would flatten any initial curvature, setting the universe near critical density. Yet the coincidence persists. We exist in a brief cosmic era when matter and dark energy have comparable influence. This reasoning assumes we are alone in the cosmos. But what if other universes exist, each with its own expansion history? In eternal inflation models, our universe is just one bubble among countless others, each with its own physics, constants, and evolution. Some bubbles may already have collapsed, others might expand faster or slower than ours, some approaching big rips, others heat death. In the quantum many-worlds interpretation, every measurement spawns infinite realities, each expanding along its own trajectory. Parallel versions of you experience every conceivable cosmic fate. Expansion raises fundamental questions about information and meaning. Every thought, memory, and arrangement of matter exists in space. Cosmic expansion stretches these patterns over vast scales. Yet quantum mechanics offers hope. Entangled particles maintain correlations across any distance, potentially preserving information indefinitely. But as regions become causally disconnected, information fragments, isolating cosmic bubbles. Locally, patterns decay, but globally, the universe encodes its expansion history in the cosmic microwave background, galaxy distributions, and space-time structure. Expansion becomes a process of cosmic memory, even as local information fades. Acceleration adds a further twist. Eventually, light from distant galaxies and the cosmic microwave background will redshift beyond detectability. Future observers will see only the local group of galaxies, isolated in empty space, and may conclude the universe has always been small, static, and eternal. They will lose evidence of the Big Bang, expansion, and distant structures, facing a profound epistemological crisis. Even their knowledge of physics' early laws will vanish, leaving only traces in ancient stars. This highlights the fragility of cosmic perspective and raises the possibility that we, too, might be limited by our observational epoch. As expansion continues, star formation will cease. Existing stars will burn out, black holes will evaporate, and the universe will approach perfect heat death. Any surviving observers will confront a cosmos stripped of its history, seeing only a few particles drifting through vast emptiness. The progression from richness to emptiness reflects the ultimate question of expansion. Does it require a destination? Perhaps not. Expansion may create meaning through temporary complexity, not permanence. Galaxies, planets, and life exist because expansion provides the dynamic stage for emergence. Without it, the universe would collapse or remain frozen. This leads to the deeper insight: what does the universe expand into? The question is like asking what's north of the North Pole. Expansion doesn't grow into pre-existing space, it creates space itself. There is no outside. The universe defines what outside means. Expansion constructs the framework for spatial relationships, bootstrapping reality into existence. Each cubic inch of new space creates possibilities for matter, energy, and complexity. The universe is not traveling toward a goal. It is generating potential. We are part of this process. Consciousness, questions, and curiosity are expressions of the universe coming to know itself. Expansion is not separate from us, we are expansion. Space, time, matter, and energy organize into patterns complex enough to contemplate their own existence. The universe expands into itself, providing infinite room for possibilities, including beings capable of awe and reflection. The question, what does the universe expand into, thus transforms. It is no longer a puzzle to solve, but a celebration of existence. The universe expands into mystery, wonder, and endless potential. We are the universe asking about itself. We are expansion itself, marveling at the infinite creativity that brought us into being. In this recognition, cosmic expansion is both process and participant, mystery and revelation, stage and actor. It is the universe becoming aware of itself, and we are part of that magnificent, impossible process.